just want to make sure you guys understand it's not true. All right, so let's talk about some of these other types of problems, again, involving justification of a subset or element stuff. Okay? So, is 13 a subset of ZI?
Yes.
No, that's absolutely false. That's not a set. 13 is not a set. Do I see squiggly brackets around 13? I don't see them. Okay? That is not a set. That is an element. So, this is false. See, you guys think you know everything. You know this. Right? That is false. Okay? 13 is an element. It is not a set. Okay? So, false. 13 is not a set. Okay? However, what about 13 is an element of
true.
ZI? That's true, right guys? So don't be so quick to make sure, or don't be so quick to assume that you know everything with the set stuff, okay? Make sure you look at the syntax of it, okay? It's very, very crucial that you guys do that, okay? And I'm not trying to insult you guys, I just want to make sure you guys remember that and don't do it again, okay? So that's true, okay? And just because it is what it is. We don't have to justify true for this, okay? So on the homework, guys, if it's true, you just write true. You don't need to write anything, okay? Is 13 in squiggly brackets a subset of ZI? Yeah, that's true. Okay, so this is true. There we go. Good stuff, guys. Okay. Now be careful with this one. Okay. Letter D. Is 13 in squigglies a subset of set 13, set 14, set 15, set 16?
No.
It is not. Okay, so that is false. Okay. What would make that true, guys?
If it is only 13,
Well, no, if it was only 13, it would definitely not be true.
If you put another set of brackets around.
Another squiggly around it, okay? Because it would have to be set 13, okay? Basically, guys, another way to make this true is if you said set 13 is an element of that, right, guys?
Yeah.
Okay?
Or
So-
if there was, each number didn't have its own.
Right, if it was only 13, 14, 15, 16. There's other ways to make it true, but unfortunately that one's going to be false, is because set 13 is actually an element of this set. Okay? So now we kind of start getting into the idea of what's the difference between an element and a set. Okay, that's basically what these problems come down to. Okay, so just be really careful, guys, with these. Okay, does everyone understand though why it's not a subset of that? It's only because we don't have the double squigglies. Okay, we need those. So if I asked you in letter E, is set 13 a subset of 13, 14, 15, 16? What would you guys tell me for that? That is true. Okay, so this guy's true. We don't need a reason for that because it's true. It just is what it is. Okay. In fact, James, I think you just said that, right?
Yeah.
So.
I mean, it's built down though.
That's okay. Alright. I think we've already answered this one as well for F. Okay, what do we think about set 13? Is that a subset of set 13, set 14, set 15, set 16? Yeah, it is. Okay, so this one's true. Okay. Is set 13 an element of set 13, set 14, set 15, set 16?
Yes.
Yeah, that's true, right? Guys, when it's an element, it means it must look exactly like what's inside it. Okay, so this would be true. Okay. This guy's missing a squiggly, so if you guys would be so kind as to fill in the squiggly right there. Sorry about that. Okay. And then the last question we have is 13 an element of set 13, set 14, set 15? It is not. It has to look identical to what's in there, and it does not. So false. Okay. 13 would be an element of 13, 14, 15, 16, okay, but not set 13, etc. All right. So let me give you guys a minute to copy those down, okay? But everyone is aware of like the level of parentheses, okay, and the level of brackets and all that stuff. That's all we have to be cognizant with this, okay? Other than that, it's pretty easy once you start getting the hang of it, okay? So remember, for an element, it has to look exactly like what's inside there. For it to be a subset, it has one more level of parentheses than what's inside there. That might be a way to think of it. Alright guys, let's just go ahead and do some stuff with the sets of numbers that we already know, our integers, wholes, rationals, etc. Okay. So let's say for some reason, I let u be all integers, I let a be wholes, b be naturals, c be odd, d be evens, okay? Let's answer the following in terms of universe A, B, C, D, if possible, okay? So if we can, we will, if we can't, we can't, okay? So if I took the odd integers and subtracted out the even integers, okay, what would I have left? The odd integers, which would be what? C. So this would be equal to C. Okay. So does that make sense to everybody, guys? When I say answer in terms of A, B, C, D, U, that's what I mean. Okay. If I have the whole numbers and I intersect that with the natural numbers, okay. Now that one we can't necessarily do a set for, but what would I be left with? A intersect B. Oh
Natural
no,
numbers.
I lied.
Yeah,
I'm
B.
sorry.
That's natural numbers.
Yeah, that would be the natural numbers, right? In fact, guys, anybody remember what's the difference between whole and natural?
Counting numbers. Natural numbers are the counting numbers.
Right. What does whole
Zero,
numbers have
zero.
that natural doesn't?
Zero.
Zero, right? So basically, A intersect B would be the natural numbers. Okay. So remember, whole numbers start at 0, natural numbers start at 1. Okay. If you don't remember that, I think a long time ago we wrote that in our notes. So go back when we were defining sets and look those up. Okay.
So natural numbers don't have zero.
That's correct.
Would it be, if A's intersecting B, would it be whole numbers then? 'Cause that-
No, that would be the union between those. When we say intersect, it has to be in both
Okay,
sets.
okay, I was thinking
Okay.
it wrong again.
But Greg, you're foreseeing into the future, maybe about 5 seconds, because A union B is set A. Okay, so does that make sense
Yeah.
now? I think you were thinking the other way.
I was.
That's okay. So just don't do that on the test, and you'll be fine. Okay. And then the following, or the final one we have, universe minus the whole numbers. Okay. This one might be tricky for us to be able to put in terms of one of those, but anybody think they might know? Well, let's say, what's it equal to first of all?
Rational numbers.
Not rationals, but negative integers and probably, well, since we're subtracting a whole number. No, you're right, it's negative integers. So couldn't we do what? U minus? You're right, sorry about that, John. I thought we were subtracting out naturals. But yeah, that would be U minus if you wanted to write it. You could just write out negative integers if you wanted to. Okay. Does that make sense, guys? Like trying to write sets in terms of the other sets that exist. Okay. Just to remind you, and I'll write this out. Okay, you can just write this off on the side. But whole numbers, 0, 1, 2, 3, da 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 da. Natural numbers, 1, 2, 3. So that way when you guys go home and do your homework, you guys remember how to do that stuff. Integers are -2, well, dot, dot, dot. -2, -1, 0, 1, 2. There we go. Okay. So just in case you guys forgot about the sets, okay, that would be the roster form of those sets, so that way you guys can write those out. All right. So, no questions about set stuff, guys. Anything I can answer about those? Okay. Now, unfortunately, okay, now that we know the preliminaries about sets, unfortunately now we have to start proving some stuff with regard to sets. Okay. So, the only rules that we're going to have available to us are these things called the procedural definitions. Sometimes they're called the axiomatic definitions of sets. I don't know if you guys know what an axiom is, but an axiom in mathematics is something so fundamental that we just accept it. We can't even prove it, okay? Like for instance, an axiom that everybody in this class understands is the number 1, okay? We define a singular element as 1 for anything. It just is what it is, okay? So that's an axiom. It's so low level and so fundamental we just assume it true, okay? Which is different than something like a lemma or a conjecture or something like that. A lemma is something that we can't disprove, but we can't necessarily prove as well. Okay, so it's just that we don't have the capabilities yet. Okay, and then theorems are things that we can easily prove. Okay, or just prove. Let's just say that. So yeah, you guys have probably heard those terms used, right? Lemmas, theorems, conjectures, you know, axioms, those sorts of things. So there are subtle differences between them. So I mean, I don't care if you guys know them or not. I mean, I do, but I don't. So anyway. So I want to go ahead and show you guys how we can use these procedural definitions, okay? And these, again, these are so fundamental that we accept them as true, okay? If we have the union between two sets, x is in A or x is in B, if we have the intersection between two sets, x is in A and x is in B, set difference means that it's in A, but at the same time it's not in B, and then the complement means that every element x is not an n. Okay, and by the way, x is just some element in the universe. Okay, so let's define what x is as well. X is some element in the universe. Alright. Now, to be able to prove that two sets are equal to one another, okay? And we're just saying that, I mean, it'd be obviously easy to do if they were finite sets, okay? But if they're just some theoretical sets, what we would have to do is we would have to show that each of the sets are subsets of one another. That's how you prove that two sets are equal to one another, okay? Which method of proof that we know of already might be helpful to show that these two conditions might be true? By cases. Nice, Ryan. Guys, if we can prove this by case 1, showing that A is a subset of B, and showing that B is a subset of A in case 2, then we'd be good with this, okay? So it's not like some of the things that we've done already are going away. It's just we're going to approach them now from a set standpoint. And I know you guys are thrilled to do proof by division into cases, but unfortunately we're going to have to suffer through it, okay? So all we have at our disposal are going to be our procedural definitions. We can also use some of the rules of logic as well. So remember we had, at the beginning of the course, we had those Boolean rules of logic, and we've already proven all of those, okay? So we can use them as well, okay? So we can also use, I'm going to write at the top, the logic rules as well. Okay. So let's go ahead and prove something very, very basic. By the way, these are actually equivalent to some of those rules we were doing with the Boolean rules. Like for instance, we proved like, I'm trying to think of what we proved using truth tables in class. We probably proved De Morgan's rule, or we proved something like that, okay? Or you could prove it using a truth table. That's actually what we're doing right now, is we're proving the most elementary of the set methods, so that way later we can use more stuff for sets. All right, so let's say we have a set, or two sets A and B, okay? I want to prove basically a commutative property. If A is intersected with B, it's the same as B intersected A. Okay. Let's define A and B to be arbitrary but particular sets, and let's let X be some element in the universe. Okay, so that's how we can start these out. Okay, so let's let A and B be sets. Doesn't matter what sets they are. They could be null sets. They could be everything that exists in the world. Okay. And let's let X be an element in the universe. Okay. And I'll put in brackets our favorite space uptaking thing, arbitrary or particular. By the way, guys, these proofs are very, very low level. Okay, so when we do these proofs, you probably, some of you guys are going to be thinking way higher than what's necessary with this stuff. Okay, go ahead, James.
Arbitrary but particular applies only to X there, right? Because A and B is a set.
Well, they could be arbitrary but particular sets as well. So like A could be like, if it wanted to be, A could be whatever set it wants to be. Okay, so when we say arbitrary but particular, we mean sets and elements as well. Okay? Because remember, we're trying to prove this true for all sets A and B, okay, no matter what. Does that make sense, sir? It's a good question, by the way. All right, case 1. Now, I'm going to write out what case 1 is we're trying to prove. What we're trying to show is we're trying to show that A intersect B is a subset of B intersect A. Okay? Because remember, what we said before, when we're trying to prove two sets are equal, we need to show that one set is a subset of the other, and then the other is a subset of the first. Okay. We already know A and B are sets. Okay. So we can say A intersect B is equal, and guys, don't we already know by procedural definition that this is equal to, or I'm sorry, stop that. We're gonna say, let's let X be an element of A intersect B. I apologize. So we're just assuming that X is just some element in the set A intersect B. Okay. Can we use the procedural definition? Okay, so we can say by procedural definition, in other words, one of those definitions up top, couldn't we say that X is an element of A and X is an element of B? And that's the definition that we just used, okay? So this is the definition that we're using right here, okay? And we said that that's fundamental, okay? We have to assume that that's true. Okay, so everyone's okay with that, guys? Not too difficult. Okay. Now, what I'm trying to eventually show is I'm eventually trying to show that X is an element of this guy right here, B intersect A. Okay? So, couldn't I flip the order of these around? Couldn't I say, thus, X is an element of B, and X is an element of A? So in other words, all I did was I just flipped around the order in which I presented the two sets. Okay? Now, what allows me to say that?
Commutative.
Commutative law of logic, right guys? Remember we had the logic law like way at the beginning of the course? In fact, if you guys have this sheet with the Boolean laws or the Boolean logical equivalencies, you guys would see that the first law that we have there, P and Q equals Q and P, that's why it's completely legal. So what you guys might want to do is try to resurrect this because we're going to be using this on occasion to be able to prove stuff. And we've already proven all of these.